Hello, welcome to my video, and today I'll be discussing about the pipe and then notation in Python as well as functional programming in Python. Just a remark that the techniques from this talk are inspired from the language F sharp, and this is an update to my previous talk on the then notation in Python. My name is Haibin. I'm currently a data engineer at a hedge fund. I have a master's degree in mathematics. I also used to work as a financial engineer and a business analyst. Previously in my talk about the then notation, as well as the pipe forward notation, in our previous talk, our goal is to put an input x through a series of functions, through a series of machines to give us the final result. In usual mathematics as well as conventional programming, we would write something like this: f g f of x. So it's okay, this notation is good, but on the other hand, you notice that the order of this function in this notation on top is different from the order in this picture. You see hgf, whereas in this case fgh. Ideally, it would be great if we could write it in this step-by-step instruction, similar to a cooking instruction, where you start off with X, step 1 do F, step 2 do G, step 2 do H. It makes it a little bit easier to understand for non-mathematics or non-programmers. And in my previous talk, I demonstrated that it is achievable using the then notation that I created. The then notation that does something like this. That looks something like this. And I demonstrated this notation with a few sample problems from Project Euler, which are some mathematics and programming challenge problems. So let's demonstrate question 1. From 1 to 999, find the sum of all the numbers that are either multiples of 3 or multiples of 5. So you can either do this question using a for loop, list comprehension, or pandas if you want to. But I advocated for this then notation with the benefit of this is that it looks similar to English. It has a line-by-line translation with English. For example, over here, you start with 1 to 999. You keep the numbers that you want. You sum up the remaining numbers, and then you print the result. So it is very similar to a step-by-step instruction, similar to a cooking instruction or cooking manual. So let's do a step-by-step demonstration. I start off with a list from 1 to 999. I keep the numbers that I want, multiples of 3 or multiples of 5. And then I add up the numbers. And then I print it to the console. So notice that at each step in the middle, I can stop at any time I want. I can stop here after getting the list of numbers, or I can stop here to sum them up after summing them up, or I can stop here after printing it to the console. I can stop at any point in the middle, or I can add more instructions in the middle. I can change in the order of the instructions if possible, and then it will still give me a good result. So that is another benefit, is that I can change the orders of the instruction if possible, or maybe I can add more instructions. So this is the original code that I presented before. And if we allow symbols, I would prefer to write it in this way because it's even clearer what I'm trying to do. Step 1, step 2, step 3, step 4. And in fact, the symbol used in F sharp is this pipe forward operator. This is the symbol used in F sharp. If we allow symbols in Python, then I would prefer to write it like such. But unfortunately, we cannot really create new symbols in Python. And what I have done to work around this is that I override the vertical bar operator to support the then notation. It's all well and good, but it could potentially cause trouble if other packages also use the vertical bar operator. In particular, I've seen this vertical bar conflict with Python pandas. So that could potentially be an issue. And also, I defined the then notation with this definitions with this. And this is the underlying code that goes behind the then notation, which looks quite complicated, and it's not so easy to comprehend. And so, a natural question to ask is that, is there a more Pythonic way of achieving this syntax? And that is the goal of this talk today. And now let's discuss about the star arcs notation syntax in Python. So if let's say we want to add up three numbers at A, B, C, of course we can add 1, 2, 3, it gives us 6. But on the other hand, if we supply too little input, for example, I only supply 2, or I only supply too many inputs, 1, 2, 3, 4, 5, both of these will give me errors. However, if we allow the star arcs notation or syntax in Python, and in fact we can do that, and we define it like such, and then we can, with this notation, we can add in as many or as little inputs as we want, and it will still compile, it will still be good and give us result in the end. So now that with this star arcs operator, this star arc syntax, how can we apply this to simplify the then notation and achieving the pipe notation that I intend to discuss? So let's go back to our previous problem. We have an input x that we want to pass through a series of machines, a series of functions, fgh, to give us the result. Ideally, it would be great if we can rewrite this into a step-by-step instruction like this, fgh. It would be great if we could rewrite this into a step-by-step instruction. So let's analyze. In this example, we have an input x as well as a series of functions fgh. So we want our pipe notation to include the input x as well as a series of functions fgh. Notice that I'm using the notation fs because it's inspired from F# and Haskell, that if we have more than one apple, we would call it apples. If we have more than one computer, we'll call it computers. And we have more than one function, and functions are usually denoted f in mathematics, we'll call it fs. So that's why I use the symbol, the name fs over here. And with that, defining this pipe, what this pipe function does is actually quite easy, as long as you use a temporary variable here, and you update the temporary variable each time you go through the function fgh. For each function, you update the temp variable and you return the final result. So straight away, this definition of pipe is actually quite easy to understand. And how do we use it? So we will use it by writing something like this. Result is pipe x fgh, which looks similar to the order of this diagram over here. Also, alternatively, we could also write it in multi-lines that look something like this, x fgh. By writing it like such, it will look similar to this step-by-step instruction over here. Previously, you want to write it in this step-by-step instruction, and by using the pipe notation, we do get it in some sort of like multi-line that looks like this. And how does this compare with the then notation? Previously in the then notation code, it looks something like this. And if I write it in pipe notation, it would look something like this using the pipe notation. What are some similarities between these two notation is that you can see that the step-by-step instruction is still written in multi-lines. It's still doing step 1, step 2, step 3 in order and written like such. But the glue that glues them together is slightly different. Previously, we used the then notation or like a symbol to connect step 1 and step 2, step 2 and step 3. Whereas in this example, we connect all of them within a pipe environment. So we use a pipe as well as some commas over here to connect these instructions together. So there are some similarities, there are some difference. Let's do a demonstration to see how this works. And so now I'll do a demonstration. In my previous talk, I've tried to solve the first 10 problems from Project Euler using the then notation. So you can see that in this code, I use then, and then. This is what I have done before. So if I run this code, you can see that this code runs perfectly fine and it gives me these results. So far, so good. Now let me try to attack the problem using the pipe notation. So notice that I change all the then notation to the pipe notation over here. So all of these instructions are connected with the pipe notation. All of these instructions are connected with the pipe notation. And so if I run this code, you can see that the code runs perfectly fine as well. And it gives me these results. So this is how I write the code in pipe notation, compared with how I write the code in then notation. So after this demonstration, let me do a pros and cons analysis of the difference between then and pipe. Just a reminder that I would prefer to write my then notation with symbols if possible, but because I could not write new symbols in Python, I have to override some symbol. I have to override the vertical line symbol. If I can write it in symbols, I would prefer to write it with this arrow. So if I do a comparison with the then notation with the pipe notation, I want to use an analogy using the plus symbol. So you can see that this is very similar to the plus symbol, whereas this pipe is very similar to the add function over here. In my opinion, I think the then notation feels more natural because the then notation looks like this, the pipe notation looks like this. Then is easier to chain. For example, you can see that to add 1, 2, 3, 4, 5, you can add up the first 4 results, then you add 5. You can just put a bracket here and it still feels natural. Whereas if you want to break up this evaluation into 1, 2, 3, 4 plus 5, I have to write it in this following form, which is a little bit verbose. It's a little bit too much word. The infix notation, the plus symbol, feels natural. It feels like primary school mathematics or secondary school mathematics. It feels natural. And also the then notation has a clear direction, where you can take a look at this then notation and the pipe notation. Visually, this looks clearer. You have a clear direction from the left to the right hand side. Whereas this notation over here, it does not convey whether you want to go from the left to the right or right to the left. There's no visual information that tells you should go from which step to which step. So these are like advantage to the then notation. But on the other hand, pipe notation, this notation is much more Pythonic. Because Python doesn't allow me to create new symbols, so I have to implement it in this following way. I have to create these arrows by using the then notation over here, This could potentially lead to problem if there are other Python packages that use this vertical line as well. So that could potentially be an issue if other packages also use this vertical line, which conflict with the then notation. And also the implementation for pipe is much easier. If you take a look at this code, it's relatively easy to understand. It's quite easy to understand. Compare with the implementation of the then notation. How do I define then? It's this very messy code that involves overwriting the vertical line symbol. In that sense, the pipe notation is much easier to understand. And now I want to discuss about having a list of instructions using the star notation. Previously, we mentioned that the star notation or the arcs notation allows for more flexibility. Of course, this flexibility is a double-edged sword. If you use it nicely, it's good. If you use it badly, it could potentially hurt yourself. But in our case, we want to do a demonstration. For example, if you want to create a function that takes a list of numbers and calculate the product. Of course, you can easily implement it using a for loop like this. That's easy. On the other hand, you could use the pipe notation that we have before. And then we do this star of a list. And this would return the same product function that is achieved using the for loop, where I might need to create like a multiply with subfunction. How does this code work? This code works by piping the starting input 1 with an arbitrary number of steps or instruction over here. Here I use star of a list of instructions. And so let's demonstrate how this could be useful in using, let's say, Project Euler question 5. Project Euler question 5. What is the smallest integer that can be divided with no remainder by all numbers from 1 to 20? So we want to find the smallest integer, the smallest number that can be divided evenly, divided with no remainder by all numbers from 1 to 20. I will assume that you know how to calculate the lowest common multiple of two numbers. So given two numbers, what is the lowest number that can be divided by both of those numbers? Which I will assume that you know how to do it. You could achieve it by calculating the highest common factor of the greatest common divisors of two numbers, and that comes from Euclid's algorithm. So let's go back to our original question. It would be helpful if we work on this problem on a step-by-step basis. Step 1, let's calculate what's the smallest integer that can be divided by 1 and 2. The answer is 2. And then after calculating this, what happens if we add one more number, 1, 2, 3? What is the smallest integer that can be divided by 1, 2, 3? And how does the result from step A help in the result of step B? How about 4 numbers? Let's say I want to calculate the smallest integer that can be divided by 1, 2, 3, 4. How does the result from step B helps in calculating the result from step C? So one solution would be to use the for loop over here. I use a temp variable over here, and then I update this temp value for each number from 1 to 20. So you could do this. Alternatively, you could also use the pipe notation, where you start off with the number 1 and then you LCM with all these numbers x for x in 1 to 20. So this way of writing things is a little bit easier because it is somewhat similar to somewhat similar to this style of thinking. So you start off with 1, 2. What happens if you got the next number 3? What happens if you get the next number 4, etc., etc.? So you start off with a starting value 1, and then you LCM it against this range of numbers. And so this would be a different approach to this problem. So how does it work? Imagine that I have 3 functions f1 and f2 and f3 that takes x and return x plus 1, x plus 2, x plus 3. And I can use the pipe notation like such, where I start off with 100, then I add 1, I add 2, I add 3, using function f1, f2, f3. On the other hand, I can also create a new list of functions over here, fs, and then I put up these functions f1, f2, f3 within the same list. So fs is a list. Then I pipe the number 100, the starting value 100, through this list of instructions. Fs is a list, so I pipe it through this list of instructions. So let's do a demonstration. So you can see that in this example f1, f2, f3, and I pipe 100 through this list of instructions, and then I print out the final result. And you can see that the final result is 106 as expected. I have add 1, add 2, add 3. I pipe the 100 through this list of functions and print out the result. It gives me 106. And so that's how this star notation could potentially be more flexible and makes it work. And so the conclusion is that previously in my previous talk, I tried to use the then notation to solve problems. But on the other hand, perhaps a more Pythonic way of implementing this would be the pipe notation. So you can see the similarities between the then notation and the pipe notation. And also a benefit of the pipe notation is that you could also pipe in a list of instructions, where by using the star notation, I pipe in a list of instructions for it to go through. And the implementation for the pipe is relatively easy. The implementation is just like this. Compared with the then notation, the implementation of then is much more complicated. This is much easier to digest. And that is the end of my presentation. If you have any questions, feel free to leave in the comment section below, and thanks for watching my video.